Welcome to tutorial 6, where we're going to talk about the thermohaline circulation. As discussed in the previous tutorial, one way that the waters of the ocean can move is because of wind forcing. But in addition to moving because of wind, they can also move because of density differences. We can see this from the equations of motion on the bottom right of the slide here. We won't worry too much about the specifics of the equation, but I just want to point out that the du by dt term, which is on the left, can be seen as the acceleration of the fluid, which in this case would be seawater. And then we can just think of every other term as things that would affect this acceleration. So for example, the far right term is friction, and this is how we would see the role of wind come in and affect the fluid. And we can also look at the equation just to the right of the acceleration term, which is a gradient of pressure term. And so we see that fluids move because of gradients in pressure, and we can think of density differences as basically setting up these pressure gradients. So in addition to moving because of wind, we also see that water would move because of pressure gradients, which is affected by these density differences. So as we're going to talk about more on subsequent slides, density in the ocean is determined by temperature and salinity. So water movement that's because of density differences is termed the thermohaline circulation, where thermo relates to temperature and haline relates to salinity. On the left is a simplified schematic of the thermohaline circulation, which is sometimes termed the global conveyor belt. So the red parts of this circulation denote the warmer surface waters, and the blue parts denote colder, denser, deep waters. And so we see that this kind of wraps all around the globe, but we could focus on specific regions. For example, in the Atlantic, we see that there's, generally speaking, a northward warmer surface flow and then a southward return deeper flow. And this is something that we will also talk about more in subsequent slides. So as we were discussing before, density in the ocean is determined by salinity and temperature, and these combine in something called the equation of state to determine density. So the plots that are shown here are actually plots that you will be making in the tutorial after this. The left is surface temperature and the right is surface salinity. They're both a mean over the period 2014 to 2016. So if we start by looking at the left plot, where we're looking at surface temperature, we see, for example, that it's warmer near the equator and cooler near the poles. And this makes a lot of sense. Sea surface temperature is affected by heat exchange with the atmosphere, which is kind of the similar temperature gradient that we would see in the atmosphere. And then on the right is sea surface salinity, and we can see that some regions are saltier, more yellow, and some regions are fresher, more blue. And one of the main things that affects sea surface salinity is evaporation and precipitation. So regions that have a lot of evaporation are going to be saltier, and regions that have a lot of precipitation are going to be fresher. And I should note, these are both made using echo data from NASA. So as we said, that these combine in an equation of state to determine density, so those two plots that were shown on the previous slide would combine to create the density plot that is shown here. So we see that more white colors are less dense and darker colors are denser. And we can see that this is just the surface, but we can see that there are gradients in density. For example, in the Atlantic, near Greenland, for example, it's quite a bit denser than if we looked near the equator. The last thing I want to talk about is the meridional overturning circulation. This is a circulation that's important for things such as heat transport across the globe, and it's typically thought of as part of the thermohaline circulation. In the Atlantic, this is called the Atlantic meridional overturning circulation, or the AMOC. So we can see this circulation on the plot on the left. This is a zonal mean view, which means that it's mean across longitudes. So here the x-axis is latitude and the y-axis would be depth. And we're not going to focus on many of the arrows, we're just going to look at the blue arrows, which are showing the circulation. So generally speaking, we see that there's an upper cell and a lower cell. We're really only going to focus on the upper cell here. And in the upper cell of the circulation, water flows northward, it sinks in the North Atlantic, and then it returns southward at depth. And that's why this is called the meridional overturning circulation. Meridional means that it's in the north-south direction, and we can see that it overturns in the sense that it sinks in the North Atlantic and then returns at depth, and then comes back up to the surface in the Southern Ocean. Traditionally, the upper cell of the AMOC has been thought of as a buoyancy-driven circulation, which means that it's driven by density differences, as we've talked about. This is largely true, but I think it's also important to note that there's impacts of the wind-driven circulation, which you talked about in the previous tutorial. So for example, the northward flow out of the Southern Ocean, which would be kind of on the left side of this plot here, is largely driven by Ekman transport because of westerly winds. There's also impacts from the gyre circulations in the subtropics, etc. So that covers the introduction to the thermohaline circulation that we wanted to talk about, and also the introduction to density in the ocean. As I mentioned, the tutorial is going to go over computing density yourself from data. I hope you have fun with it.